In many physical systems, we find structures that maintain their stability in highly dynamic environments. These structures, whether they are ocean waves, optical pulses, or quantum field configurations, exhibit a form of homeostasis that allows them to persist despite the complex forces acting upon them. Traditionally, we might categorize such stability under the umbrella of nonlinear dynamics, but today, we will explore a deeper, more structured interpretation. We will delve into triadic logic, a framework where stability is not just an accident of balance, but a product of interdependent relationships between multiple elements. When we think about topological stability, we are often referring to phenomena like solitons, localized waves that maintain their form and energy over long distances. These self-sustaining waves defy traditional expectations of dissipation and decay. In quantum chromodynamics, QCD, the theory that governs the interactions of quarks and gluons, similar stable configurations arise, such as hadrons, protons, neutrons, and even more exotic objects like instantons or skyamions. These configurations, I propose, are not merely nonlinear, but can be more precisely understood as self-sustaining triadic systems. Today, we will explore how the triadic structure of QCD interactions can provide new insights into both the homeostatic balance of these systems and their stability. To begin, let's explore how the basic elements of QCD, quarks, gluons, and hadrons, exist not merely in isolation, but as parts of a self-sustaining triadic system. In QCD, quarks are never found free in nature due to the phenomenon known as color confinement. This means that quarks are always bound together in groups, and the force that holds them together is mediated by gluons, the carriers of the strong force. These bound states of quarks and gluons form the hadrons, protons, neutrons, and other particles. In a triadic sense, we can describe this interaction using coexistence, where the stability of the system arises from the mutual interaction of all three elements. Quarks, A, interact with gluons, B, gluons mediate the formation of hadrons, C, and hadrons are the structures that house quarks. Each element depends on the other two to maintain the system's overall stability. This is not just a simple pairwise interaction, but a fully interdependent network where quarks, gluons, and hadrons exist because of their relationship to each other. Imagine trying to remove one part of this triad. Without quarks, there is no need for gluons, and without gluons, hadrons cannot exist. Thus, their coexistence is key to the formation of stable particles in QCD. This balanced interplay mirrors the behavior of solitons, where the nonlinear effect of energy concentration is balanced against dispersion, maintaining the soliton's form. What this suggests for QCD is that stability, whether in solitons or hadrons, might be better understood through this triadic logic of interdependence, rather than merely classifying it as nonlinear. By viewing QCD interactions as a stable triadic system, we unlock new possibilities for modeling interactions within other dynamic systems where stability arises from interdependence. Now that we've seen how coexistence creates stability, we need to explore what happens when this balance is disrupted. In triadic logic, equilibrium examines the consequences of imbalance, when one or more components of the system are removed. In QCD, if the binding force of gluons collapses, the confinement of quarks is broken, and hadrons fall apart. This can be understood in the context of extreme environments, such as the quark-gluon plasma that forms in high-energy collisions, where quarks and gluons no longer form hadrons and instead exist as a free, unbound plasma. This equilibrium breakdown reflects the same logic that governs soliton disintegration in physical systems. If the balance between nonlinear concentration and dispersion is disrupted, the soliton dissolves and the energy spreads out. In QCD, the removal of gluons, the binding force, causes the entire triadic system to collapse, reinforcing the idea that stability in such systems depends on continuous interaction. The implications of this are profound for understanding other high-energy processes, like those in early universe physics or inside neutron stars, where we might witness a breakdown of confinement and the release of free quarks and gluons. These insights suggest that stability in QCD, and indeed in other complex systems, depends on maintaining this delicate triadic balance. Let's move from equilibrium and breakdown to a deeper reflection on how stability is reinforced through harmonic interaction. In QCD, the interplay between quarks and gluons within hadrons can be thought of as a resonant harmonic system, where each component reinforces the others. In triadic logic, this is captured by a harmonic pattern. Here, the relationship between quarks, gluons, and hadrons behaves much like a harmonic oscillator, where the energy and forces between the components are perfectly balanced and self-sustaining. When quarks and gluons come together, they form hadrons, and this hadron structure reinforces the need for the quarks to remain bound. The interaction of these components stabilizes the system, much like the harmonic stabilization of solitons, where waves maintain their form due to resonant, self-reinforcing dynamics. The key takeaway here is that systems exhibiting harmonic interaction are self-reinforcing. In QCD, we can see hadrons as harmonically stabilized solitons, where the internal interactions create a self-sustaining field. This opens up interesting possibilities for exploring other areas of physics where harmonic interactions might be at play, such as in condensed matter systems or even in cosmological structures. But what happens when this harmony is lost? Dissonant patterns give us a framework for understanding breakdowns in this harmonic balance. In extreme conditions, such as the very high temperatures achieved in particle collisions, the resonant confinement of quarks inside hadrons breaks down and the system becomes dissonant. Instead of stable hadrons, we find a quark-gluon plasma, where the components of the system no longer reinforce each other and instead exist in a free, unbound state. This dissonance is akin to the destructive interference of waves, where the harmonious patterns of reinforcement collapse, leading to instability. The lessons we draw from this are important systems that maintain their stability through harmonic interaction are vulnerable to breakdowns under extreme conditions, but the nature of this breakdown gives us clues about the limits of stability in physical systems. We turn now to one of the more exotic but crucial aspects of QCD, the concept of instantons and other nonlinear tunneling effects. Instantons describe transitions between different quantum vacuum states, and they emerge naturally from the intricate field interactions that QCD describes. While the interactions of quarks and gluons are often categorized as nonlinear, we can delve deeper using triadic logic, specifically nonlinear and retrospective patterns, to better understand these transitions. In nonlinearity, we focus on how changes in one element of the system drive nonlinear responses in others. Instantons in QCD are solutions that mediate the transition between distinct vacuum states, shifting from one configuration of the gluon field to another. These vacuum transitions can be understood as nonlinear progressions. The initial vacuum state, A, moves toward a new vacuum configuration, C, while influencing the dynamics of the gluon field, B, during the transition. The presence of these instanton-like structures is critical to QCD because they allow for changes in the field configuration that otherwise would not occur. This progression mirrors how nonlinear solitons in physical systems self-organize and propagate through space without dispersing their energy. The instanton connects one vacuum state to another in a similar fashion, influencing the gluon field as it transitions. Much like how solitons shift the configuration of the medium through which they move. But it's not only a forward-moving nonlinear progression. Retrospectivity provides insight into how the present configuration of the vacuum in QCD is also shaped by its past. Instantons don't just connect different vacuum states, they encode the history of field configurations within the quantum system. Each instanton transition reflects the influence of prior configurations, demonstrating how the system's past evolution directly affects its current and future states. This retrospective nature of QCD vacuum states implies that the system is never truly independent of its prior history, a profound notion that has broader implications for field theory in general. The interplay of nonlinear progression and retrospective influence invites us to explore how other quantum systems evolve. We might ask, In what other contexts do nonlinear transitions between states incorporate elements of their historical trajectory? This could offer new ways to understand not just quantum fields, but also cosmological models, condensed matter systems, or even biological processes where past configurations influence future dynamics. As we reflect on these different triadic structures within QCD, we begin to see a more nuanced picture of nonlinear systems emerge. Rather than simply viewing QCD as governed by chaotic, nonlinear feedback loops, triadic logic reveals a homeostatic structure, one where stability and interaction arise from the interdependent relationships between quarks, gluons, and the resulting solitonic configurations, such as hadrons or instantons. What does this mean for solitons in general? Solitons in physical systems, whether they be optical pulses, water waves, or quantum field solutions, are better understood as self-sustaining triadic systems. The nonlinear interaction of forces that keeps them stable, preventing dissipation, is not just a product of complex dynamics, but of a triadic equilibrium. This invites a broader application of triadic thinking to other dynamic systems in nature, where stability is often thought of as nonlinear or chaotic. For example, consider how we might model other topologically stable configurations like vortex structures in superfluids or flux tubes in superconductors, using this triadic approach. What we are learning from QCD and solitons could apply across the spectrum of topological phenomena, in systems where stability arises not from simplicity, but from the intricate, interrelated feedback of multiple interacting elements. As we conclude, it's clear that rethinking nonlinear systems through the lens of triadic logic offers profound new insights. Whether we are dealing with the forces that bind quarks and gluons inside hadrons, the stability of solitons in a medium, or the transitions between vacuum states in QCD, triadic systems provide a structured framework for understanding how homeostasis arises in dynamic environments. These systems do not just persist by chance. Their stability emerges from interdependent, balanced relationships between their constituent elements. As we move forward in our exploration of physics, mathematics, and even biology, applying this triadic lens could allow us to uncover the underlying structure that governs stability in nature. Systems we once thought of as merely nonlinear or chaotic might, in fact, reflect homeostatic triadic equilibria that ensure their continued existence. In the end, the patterns and triads we've explored today invite us to look beyond superficial complexity. They ask us to focus on the fundamental relationships that underlie the stable, resilient phenomena we see in the world, from the smallest particles to the most vast cosmological structures. This approach not only deepens our understanding of solitons and QCD, but also opens new avenues for exploring stability across all fields of study.